All right. So we are picking up in chapter 22. We've already done the calculation of flux for a not complex surface, but at least an involved calculation. The one we did in class regarding the flux through a hemisphere, and we demonstrated that the flux through that hemisphere was the same as the flux through the equivalent circle that would go through them. Okay, so now let's move on to the physics. And the physics is this guy Gauss came up with some rules, and he said, if we calculate the electric flux that is through a closed surface, if we say this is a closed surface, and you guys recall the definition of flux, you can review your notes or review the book. If you calculate this, Gauss said this is going to equal the charge that's within that closed surface divided by epsilon zero. And now what I'd like to do is take a moment to determine if this is consistent with what we already know. Well, what do we already know about the electric field? Well, we know Coulomb's laws. What we're trying to do really is figure out if Coulomb's law and Gauss' law end up giving us the same results. And if they do, then we'll say, okay, looks like we're somewhere. All right. So let's go ahead and assume the simplest possible situation, which is we have some charge Q sitting in the middle of space. And as we will do many times, as a matter of fact, any time that we use Gauss's law, we are going to take advantage of the symmetry of the situation. And the symmetry in this situation is spherical. That is, there is no way to tell by looking at the electric field what point on a sphere you are sitting at. The electric field will always be pointing outwards from the center, and it will always have the exact same magnitude, okay? And this we can actually say without knowing anything about Coulomb's law or, well, not quite. We do have to assume that the electric field is a vector. And once we assume that, then we can say this without Coulomb's law, because there is no reason for this spot to be any different than a spot here, 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 here. Okay. So therefore, we know spherical symmetry is going to hold, so this is what we're going to do. And actually, I probably should have left that, but that's all right. Okay. So now what I'm going to do, I'm going to draw two things. First thing I'm going to draw is a little dA surface element. And you guys will recall that we define this dA as a vector normal to the surface of the magnitude of the area that it represents. So this little dA, as we calculated in class, is r squared sine theta d theta d phi. Okay, so we calculated that, and in this particular case, what we're going to find out is that we don't really need to mess with that, because the only time we need to do an integral is when things are changing. But in this particular case, here's my dA. It's heading straight outward from the surface. Well, what about my vector here as relates to the electric field? So let's look at the electric field vector. And we see the electric field vector. I'm just going to move it to a difference point for clarity, that it is also radial outward from the center. And so the relationship between this EO and dA is always going to be the same. And you will also recall that E dot dA, that is the dot product of any two vector vectors, is going to equal E dA cosine theta. Okay, so the question is, as we go around the sphere, every single spot on the sphere will any of these values change? No. E is going to stay the same. dA is going to stay the same. The cosine theta is always going to be equal to 1 because cosine theta equals 0 because they're both perpendicular to the sphere. So all we need to do is just integrate. Okay, keep that mental picture in your mind. But all we need to do now is take our E dot dA just becomes the integral of E dA and, E doesn't change, and dA integrated over this is just going to give us the full area, which is 4 pi r squared, and I'll just call this E0 at this distance r. That's the value of the electric field on that sphere. And then we're done. E dot dA equals 4 pi r squared E0. Now we're going to use Gauss's law, and Gauss tells us that this is equal to the charge enclosed divided by epsilon 0. So all I'm going to do is set these two things equal. Q enclosed over epsilon 0. And, see, I'll go like that. Nope, I won't go like that. My camera had me fooled. Okay. So now all we're going to do is just some algebra because we want to determine what this E0 is. That's the whole point of this exercise. And we can just say E0 equals Q enclosed over 4 pi epsilon 0 r squared. Well, have you ever seen this term 1 over 4 pi epsilon 0? Indeed you have. That is defined as Coulomb's constant, which you guys have used many times. And so we end up with this is equal, it says E0 equals K Q enclosed over R squared. And you recall that when we looked at the drawing, we made the physical argument that E had to be perpendicular to that surface. What is that direction? That is the R hat direction. So we now have, oh, excuse me. Oh, sorry. So we now have an expression for the electric field that we derived from Gauss's law right here. We derived that, and yet we ended up right back at Coulomb's law. Oh, Coulomb's law. So that gives us a pretty high degree of confidence that Gauss's law is a pretty good representation of reality. The next step is we're going to actually go the other way around. What we did here is we assumed Gauss's law was true and figured out what that said about Coulomb's law. Now we're going to assume that Coulomb's law is true, and what does that say about Gauss's law?